We all wonder about it. What if I had made a different choice? What if I had taken that other job, or never met that person, or turned left instead of right? As we play out these alternate histories in our minds, it's a very human thing to do. We tell stories about it, we make movies about it. The idea of other worlds, other versions of ourselves is everywhere. And for a long time, that's all it was, a story, a fun thought experiment, but somewhere along the way, something changed. The idea of a multiverse, of other universes, leaked out of science fiction and into science. Physicists, cosmologists, the people who study the very nature of reality started talking about it seriously. Not all of them, of course. Many think it's nonsense, but many others think it's not only possible, but likely. Even inevitable. So, what's the deal? Does the multiverse truly exist? The honest answer is we don't know. There is no proof, not a single shred of hard evidence. We can't point a telescope and see another universe. We can't send a probe. So why are we even talking about this? It's because the idea of a multiverse isn't just something scientists made up for fun. It pops up uninvited from our best theories of the universe. It's a side effect of the math we use to describe reality. It's like we're trying to solve an equation about our own house, and the answer keeps telling us there's a whole neighborhood we can't see. That there isn't just one multiverse theory. There are a few different kinds, and they come from different parts of physics. Some are easier to wrap your head around than others. Some sound like they're straight out of a comic book. But they all start with what we know, or what we think we know, about our own universe. And to understand them, we have to start there. We have to start with how big our world really is. Think about the universe, the Earth, the Sun, our galaxy, the Milky Way. We used to think that was it. But we built better telescopes. We saw other galaxies, billions of them, and then we realized we could only see so far. There's a limit. Not because the universe ends, but because it started. The Big Bang happened about 13.8 billion years ago. That means we can only see light that has had 13.8 billion years to travel to us. Anything farther away, the light just hasn't reached us yet. So there's a sphere around us, our observable universe. It's huge, but it's finite. The big question is, what's outside that sphere? The simplest, and maybe the most likely, answer is just more universe. More space, more galaxies, more stars and planets. There's no reason to think it all just stops right at the edge of what we can see. Our universe doesn't have an edge. It's probably the same everywhere in all directions forever. And if space goes on forever, then you get the first type of multiverse. This is sometimes called the level 1 multiverse. It's the least strange one. It doesn't require any new physics. It just requires space to be really, really big. Maybe infinitely big. If space is infinite, then every possible arrangement of particles has to happen somewhere. Think about it like a deck of cards. There are a lot of ways to shuffle a deck, but it's a finite number. If you shuffle an infinite number of times, you're guaranteed to get every single possible order. You'll get the same order more than once. Many times, in fact. An infinite number of times. Now apply that to the universe. The particles in our observable universe can only be arranged in a finite number of ways. It's a huge number, bigger than you can imagine, but it's not infinite. So if space goes on forever, then eventually, far, far away, there must be another region of space that is identical to ours. A region with a galaxy that looks just like the Milky Way, with a star that looks just like the Sun, and a planet that looks just like Earth. And on that planet, there would be a person who looks just like you, and it wouldn't stop there. There would be an infinite number of these regions. There would be versions of you who are exactly the same. There would be versions where you chose to wear a different shirt this morning. There would be versions where you made that different choice you always wonder about. Everything that can happen within the laws of our physics does happen. Somewhere out there, across an unimaginable distance of space, another you is reading this. This is a strange thought. It feels weird, but it's a direct consequence of two simple ideas: that space is infinite, and that matter is arranged randomly within it. We don't know for sure if space is infinite, but all our measurements suggest it's flat, and a flat universe is most likely an infinite one. So, this first kind of multiverse isn't some wild theory, it's just the logical conclusion of our current cosmological model. These other universes aren't in another dimension. They're just really, really far away. So far away, we will never see them or interact with them. They are part of our same single space-time. But that's just the first step. The other multiverse ideas get weirder. The next idea comes from the very beginning of the universe. It's called the level 2 multiverse or the inflationary multiverse. Our best theory for the early universe is called cosmic inflation. The idea is that in the first tiny fraction of a second after the Big Bang, the universe expanded at an insane exponential rate. It went from smaller than an atom to bigger than a galaxy in less time than it takes to blink. This rapid expansion smoothed everything out and made the universe look the way it does today. Inflation theory explains a lot of things we see in the cosmos. It's a very successful theory. But one of its architects, a physicist named Alan Guth, realized it had a strange consequence. According to the theory, inflation might not stop everywhere at the same time. It's like a pot of boiling water. Bubbles form in the water. Inside a bubble, the water stops boiling and turns to steam. But outside the bubble, the water keeps boiling and making new bubbles. The theory of eternal inflation says the universe as a whole is like that boiling water. It's always expanding, always inflating, but in some places, inflation stops. A bubble forms. Inside that bubble, a universe like ours is born. It has a big bang, it cools down, stars and galaxies form, but outside the bubble, the rest of space is still inflating, stretching at incredible speeds, and creating more and more bubbles. So our universe is just one bubble in a vast, eternally inflating sea of space, a cosmic foam of bubble universes. Each bubble could have its own Big Bang. Each bubble would be a self-contained universe, completely cut off from the others. We could never travel from our bubble to another. The space between them is expanding faster than the speed of light. And here's where it gets really interesting. When each bubble universe forms, the laws of physics might be different inside. Maybe the strength of gravity is different. Maybe the charge of an electron is different. Maybe there are different fundamental particles. Most of these universes would be dead. If gravity were just a little bit stronger, the universe would have collapsed back on itself right away. If it were a little weaker, stars and galaxies might never have formed. Our universe seems perfectly tuned for life. The constants of nature have just the right values to allow for stars, planets, chemistry, and eventually us. This is called the fine-tuning problem. Why are the laws of physics so perfect for us? It could be a massive coincidence, it could be a sign of a creator, or if there are an infinite number of bubble universes, it's not a surprise at all. It's just that we, as living beings who can ask the question, must find ourselves in one of the universes that has the right conditions for life. We couldn't exist in any of the others. This is called the anthropic principle. We won the cosmic lottery, because if we hadn't, we wouldn't be here to complain about losing. This inflationary multiverse is a very popular idea among cosmologists. It's a natural outcome of a theory, inflation, that already explains so much about our own universe. But again, there's no way to prove it. We can't see the other bubbles. We're stuck in ours. Some scientists have looked for clues, like a bruise on the cosmic microwave background radiation, the leftover heat from our Big Bang. And a collision with another bubble in the distant past might have left such a mark. So far, they haven't found anything conclusive. So we have a multiverse where other yous live incredibly far away. And we have a multiverse of other bubble universes with different laws of physics. Now we get to the one that really messes with your head. This one comes not from cosmology, the study of the very big, but from quantum mechanics, the study of the very small. This is the level 3 multiverse, or the many worlds interpretation. It's probably the one you think of for movies. The one with branching timelines. To understand it, you have to understand a little bit about the bizarre rules of the quantum world. At the subatomic level, particles don't behave like little billiard balls, they behave like waves of possibility. An electron, for example, isn't in one specific place until you measure it. It's in a cloud of potential places, a superposition of all its possible states at once. The act of measuring it, of looking at it, forces it to choose a single position. This is called the collapse of the wave function. Physicists have argued for a century about what this collapse actually means. It's one of the deepest mysteries in science. In the 1950s, a physicist named Hugh Everett came up with a radical idea. He said, what if the wave function never collapses? What if the particle doesn't choose one path? What if, when you make a measurement, all the possibilities happen? How can they all happen? They happen in different universes. The moment of measurement is a moment of splitting. The universe splits into multiple branches. In one branch, the electron is here. In another branch, the electron is there. Each branch is a real parallel universe. And it's not just for electrons. Every quantum event, every time there's more than one possible outcome, the universe branches. This means you are splitting into different versions of yourself all the time. Right now, there's a quantum event happening in your brain. A particle can go one way or another. The universe splits. In one universe, you continue reading this sentence. In another, you decide to get up and get a glass of water. Both of those versions of you are real. Both of them think they are the real you. They share a past, but their futures are now separate. This is a staggering idea. It means there's a near infinite number of parallel Earths stacked on top of each other in some abstract quantum space. Every possible outcome of every single event has played out in some universe. There's a universe where the dinosaurs never went extinct. There's a universe where you are the king of England. There's a universe where you made every right decision, and one where you made every wrong one. Unlike the other multiverses, these parallel worlds are not far away in space. They are right here, now. But they are in a different quantum state, completely inaccessible to us. We can't feel them or see them. They are forever separate. The many worlds interpretation is beautiful in its simplicity. It gets rid of the weird, mysterious collapse of the wave function. It just takes the math of quantum mechanics at face value. The math, called the Schrödinger equation, describes how these waves of possibility evolve. Everett said, let's just assume the equation is always right and describes all of reality. The splitting is the result. Many physicists love this idea because it's clean and elegant, but many others hate it. It's not very economical. To solve one small problem in quantum mechanics, it creates an infinite number of universes. That seems like a high price to pay. And just like the others, it's untestable. How can you prove that another version of you just split off? You can't. It makes no testable predictions that are different from the standard interpretation of quantum mechanics. So, for now, choosing to believe in it is more a matter of philosophical taste than scientific necessity. There is one more major type of multiverse to consider, and it comes from the cutting edge of theoretical physics. It comes from string theory. String theory is an attempt to be a theory of everything. It tries to unite quantum mechanics, the small stuff, and general relativity, the big stuff, like gravity, into one single elegant framework. In string theory, the fundamental building blocks of reality aren't point-like particles. They are tiny vibrating strings of energy. Different vibrations of these strings give us all the different particles we see, like electrons and photons. But for the math of string theory to work, it requires extra dimensions of space. Not just the three we know: length, width, height, plus time. It needs something like 10 or 11 dimensions. So where are these other dimensions? The idea is that they are curled up, incredibly small, at every point in space. We can't see them or move in them because they are too tiny. But what if not everything is tiny? String theory also includes objects called brains, which is short for membranes. A brain can have any number of dimensions. A 0 brain is a point. A 1 brain is a string. A 2 brain is a plane. Our entire universe could be a 3 brain. Imagine our universe as a giant, 3-dimensional sheet of paper floating in a higher dimensional space, a bulk. And maybe, just maybe, there are other brains, other universes, floating parallel to ours in that same bulk. This is the level 4 multiverse, or the brain multiverse. These other brain universes could be just a millimeter away from us, but in a 4th spatial dimension we can't access. We are stuck to our brain like ants on a piece of paper. We can't perceive the other brains floating above or below us. But gravity, according to some versions of string theory, might be different. Gravity might be able to leak between the brains. This idea is exciting because it might, just might, be testable. If gravity can leak, it would mean that gravity is weaker on our brain than it should be. We could test for this by looking for tiny deviations in gravity at very small distances. Our experiments at places like the Large Hadron Collider have looked for signs of extra dimensions, like energy from a particle collision disappearing from our brain into the bulk. So far, they've found nothing. This brain world idea also offers a new story for our origin. Maybe the Big Bang wasn't the beginning of everything. Maybe it was the result of 2 brains colliding. The massive energy from that collision could have created our universe, and it could happen again. So we have 4 different ways we could live in a multiverse. One based on infinite space, one based on eternal inflation, one based on quantum mechanics, and one based on string theory and extra dimensions. They are all plausible ideas that come from serious science, but they all share the same big problem. Is this even science? Science is built on a foundation of testable hypotheses. You come up with an idea. You use that idea to make a prediction about the world. You do an experiment to see if your prediction is right. If it is, your theory gets stronger. If it's wrong, you throw the theory out or change it. This process is what separates science from philosophy or religion. It's what Karl Popper called falsifiability. A scientific idea must, in principle, be provable to be false. The problem with all the multiverse theories is that they seem to be unfalsifiable. How can you disprove the existence of a universe you can't see, measure, or interact with? You can't. If we look for a bruise in the cosmic background and don't find one, it doesn't mean the inflationary multiverse isn't real. It might just mean our bubble never hit another one. If we don't find evidence for extra dimensions, it doesn't mean string theory is wrong. It might just mean the effects are too small for us to detect. This makes a lot of scientists very uncomfortable. They worry that by embracing the multiverse, physics is moving away from testable predictions and becoming a kind of metaphysics. They argue that a theory that explains everything, because every possible outcome happens in some universe, actually explains nothing. It's not a predictive theory anymore, it's just a story. They believe scientists should focus on problems we can actually solve and test within our own universe. On the other hand, the defenders of the multiverse say this is just how science works. The Earth going around the sun was once a philosophical idea. Atoms were once an untestable hypothesis. Maybe our technology and our theories just aren't good enough yet. To them, refusing to consider the multiverse just because it's hard to test is like a drunk looking for his keys only under the lamppost because that's where the light is. The reality might be bigger and stranger than what's convenient for us to test. They also point back to the fine-tuning problem. The fact that our universe is so well suited for life is a real measurable piece of data. The multiverse, specifically the inflationary one, provides a plausible scientific explanation for it that doesn't require a miracle or a creator. For some, that makes it a more scientific idea than the alternatives. The debate is fierce, and it gets to the heart of what science is and what it should be. So, where does this leave us? We are stuck in a strange and fascinating place. We have these compelling ideas born from our most advanced physics that suggest reality is vastly larger than we ever imagined. We have the possibility of infinite copies of ourselves living out every choice. We have the idea of other universes with alien laws of physics. We have the mind-bending concept of the world splitting with every quantum roll of the dice. But we have no proof. We are left with stories. Beautiful, mathematically consistent stories, but stories nonetheless. And maybe that's the point. The question of the multiverse forces us to confront the limits of our knowledge. It pushes us to ask what it means to be human in such a potentially vast cosmos. Does it make your life meaningless? If there are an infinite number of yous, does anything you do here really matter? If every choice you make is made by some other version of you, does that mean your choices aren't really yours? It can feel that way. It can feel like you are just one tiny, insignificant copy in a sea of cosmic static. Or does it do the opposite? Maybe the existence of a multiverse makes this life, the one you are living right now, infinitely more precious. This is the only one you get to experience. The other yous are not you. Their joys and their sorrows are their own. Your consciousness, your awareness, is tied to this specific path through the branching tree of possibilities. This universe, this timeline, is your home. The fact that it exists at all, with its finely tuned laws that allow for your existence, is a miracle. Whether it's one of many or the only one, it is the one you have. The search for the multiverse is a search for our place in the cosmos. It's an extension of the same journey that led Copernicus to realize the Earth wasn't the center of the universe, and Hubble to realize our galaxy wasn't the only one. Each step has made us smaller, but it has also made our universe grander. The multiverse is just the next and perhaps the final step in that journey. We don't know if it's true. We may never know. But the question itself changes us. It expands our minds, it forces us to think big, to contemplate infinity, and to wonder about the fundamental nature of what it means to be. And that is a powerful thing, whether there is one universe or an infinite number of them. The truth is, we are here, now, in this one. And for us, that's everything.